Hi everyone. It's just a short video tutorial on one of the questions from week 8 problem set. So the question that I'd like to go over today is 10.8, 10.8 A and B. So if you understand this 10.8 A and B, then you should also be able to do 10.2, 10.9, all these questions yourself. So it's question 10.8 from week 8 problem set. This question says that a recent study found that 51 children watched a commercial for Walker Crisps potato chips featuring long-standing sports celebrity endorser, ate a mean of 36 grams of Walker Crisps compared to a mean of 25 grams for 41 children who watched a commercial for an alternative food snack. So we have two samples here. In one sample we have 51 children, and these children watched a commercial for Walker Crisps potato chips, and we have another sample here where we have 41 children, and these 41 children ate a mean of 25 grams, 25 grams of an alternative food snack. So we also have information on the standard deviation of these samples. From the first sample, we have a standard deviation of 21.4 grams, and in the second sample we have a standard deviation of 12.8 grams. Now, given all this information, assuming that the population variances are equal and the significance level alpha equals 0.05 or 5%, is there evidence that the mean amount eaten was significantly higher for the children who watched the Walker Crisps commercial? So to answer this question, we first have to write out the null hypothesis and the alternative hypothesis. So the alternative hypothesis is what basically the question says. So the question says, oh, sorry, not the right place. Here we go. Yeah. So the question says that is there evidence that the mean amount eaten was significantly higher for the children who watched the Walker Crisps? So the population mean, or the mean of the first population is greater than the mean of the second population. That's what we have to show the evidence for. So that's gonna be built in our alternative hypothesis. And in our null hypothesis, we'll have just the opposite case. That means the population mean, or the mean of the first population, is smaller than or equal to the mean of population 2. So that's what we have here. The null hypothesis H naught equals the mu1, that is a mean of population 1, is less than or equal to the mean of population 2, that is mu2. So that's equal to 0 here. Okay, yeah. And the alternative hypothesis is that the mu1 is greater than mu2 and not equal to 0. So to do this hypothesis testing, we first have to construct a t-statistic. So when you're comparing to population means, the t-statistic is written or is calculated using this formula that we have here, and this formula will be provided to you in the exam, so you don't have to memorize this. So let's just take a moment to understand what these symbols mean here, or what these letters mean here. So x bar 1 it's a mean of sample 1, x bar 2 is the mean of sample 2, mu1 is the mean of population 1, mu2 is the mean of population 2, and s square p here is the pooled, we call this the pooled variance. It's called the pooled variance. So and I'll come to this in a moment. N1 is the number of observations in sample 1, and N2 is the number of observations in sample 2. So next thing what we have is a pooled variance, S square P. So this is something that we have to calculate first, then we can plug that back in the formula for T, where we have this S square P in the denominator. So S squared P, this thing has to be calculated first. So this is a formula. This S squared P takes this form. So this formula is used to calculate S squared P. So for S squared P, we see that we have this S1 square and S2 square, these two terms here. So what is S1 square? S1 square is okay. So S1 square, I believe. So if we just plug in the standard deviation for for sample 1, so that is S1, and so S1 in our case S1 is going to be, let's just quickly go back to the question here. Here we go. So S1 equals 21.4. S1 equals 21.4 because this is the standard deviation of the first sample. Then we also have S2, which is a standard deviation of sample 2, and that is equal to 12.8 grams. This is the standard deviation of the second sample. So you plug these numbers in here, S1 and S2, and we know that N1 equals the number of observations we have in the first sample, and N2 is the number of observations we have in the second sample. So we know that we have 51 observations in sample 1 and 41 observations in sample 2. So plug all these numbers in here, and then you get the pooled variance equals 327.24. So this is a number that we're going to use in the next step, that is when we calculate the t-statistic. So let's come back to the calculation of t-statistic. So we know the value of S squared P, that's 327.24. We have already calculated that. We know the value of N1, the value of N2, so we have plugged them in here. What about the value of x bar 1 and x bar 2? So to find those out, we have to go back to the question again. So the question says that in sample 1, the children ate an average of 36 grams of Walker crisps. So 36 is the mean of sample 1, and 25 is the mean of sample 2, because if you go back to the question, you'd see that in the second sample, the children ate a mean of 25 grams. So 25 is the mean in the second sample. So we plug that in here. But mu1 minus mu2 is always going to be equal to 0, because our assumption, or the null hypothesis, it's actually built in the null hypothesis that there is no difference between mu1 and mu2, and so we just plug that in here, that 0 thing. So this is something that you always do. You always put mu1 minus mu2 equals 0 in any problems that you solve, like these ones. So once we plug all these numbers in here, I believe you should get 2.89. Now the next thing that we have to do is we have to compare this 2.89 with the critical value. We have to compare this 2.89 with the critical value. The question is, what's going to be a critical value? So the critical value in this case, because it's a t-distribution, we have to look at the number of we have to look at the degrees of freedom, how many degrees of freedom we have. Then we have to look it up on the t-distribution table, or the t-table. So in this particular exam, or in this particular question, or in these types of questions, the degrees of freedom is given by the numerator, the denominator here. So the denominator here is n minus 1 plus n2 minus 1. So this is basically nothing but, let me just quickly write it. So it's basically n1 plus n2 minus 2. That's it. This thing, so if you simplify this, n1 minus 1 plus n2 minus 1, if you simplify this, you're gonna get this. So this is our degrees of freedom. So in this question, our degrees of freedom is 51 plus 41 minus 2. So 51 plus 41, that's I believe 92, and minus 2, that just gives us 90. So that's our degrees of freedom, 90. So let me just quickly find out the t-table. There you go. Here's our t-table. So we have our degrees of freedom 90. So it's somewhere between 80 and 100, and we are looking at 5% significance level. So one tail 5%. There you go, 5%, one tail 5%. Let's go down along this column. So it's somewhere between, I guess, 1.664 and 1.66. So let's just stick to 1.66. So our critical value in this case is 1.66. But there is one more thing that I want to bring draw your attention to, is that look at this alternative hypothesis. It says that mu1 is greater than the mu2. So this is not a two-tailed test. A two-tailed test simply says that mu1 is not equal to mu2. So this is not a two-tailed test. This is rather a one-tailed test. So we need to keep that into our mind when we are trying to find out the critical value. For example, if this was a two-tailed test instead of a one-tailed test, that is, if mu1, if we had written this alternative hypothesis as mu1 not equal to mu2, if that was our alternative hypothesis, then the critical value in this case would be, here you go, we have 90 degrees of freedom, so that's somewhere between 80 and 100. That's not gonna change, so that's fine. But if we're looking at a 5% significance level, now because it's a two-tailed test, this 5% will be divided equally between the upper tail and the lower tail. So 5%, so if you divide that by 2, that's going to be 0.025. So instead of looking at this column, which we did previously, just a few minutes ago, or just a few seconds ago, we will be looking at this column here, 0.025, for 90 degrees of freedom. So that's gonna give us somewhere, I guess, around between 1.99 and 1.98. So maybe we can just stick to 1.98 or 1.99. Doesn't really matter. Both of these are very close. So the critical value would have been 1.98. But in any in our case, in this particular question, we don't have a two-tailed test. We rather have a one-tailed test. Therefore, the critical value that we will use is 1.66, because that corresponds to 0.05 significance level. Okay, let's come back to the question now. Let's come back to the workout. Here we go. So we have 2.89. So if you compare this with the critical value, which we have figured out to be 1.66, so here I have to make a little change. 1.66. There you go. The decision rule is if the t-statistic is greater than 1.66, we reject the null hypothesis. So in this particular question, this is actually the case. The t-statistic that we have found out is 2.89. It's definitely greater than 1.66, so we reject the null hypothesis. So in this question, we can say that there is enough evidence that the mean amount of Walker Crisp crackers eaten was significantly higher for the children who watched food ads. So that's the answer to question number 9.8a. Now we will do question 10.8b. So let's have a look at the question first. So 10.8b, here we go. Here's the question, 10.8b. Assuming that the population variances are equal, constant between the mean amount of crisps eaten by children who watch the commercial and children who watch the alternative food commercial. So let's come back to our answer for 10.8b. Here we go. So the confidence interval is always constructed in this manner whenever we are comparing two sample means from two different populations, and this formula will be provided to you. So x bar 1 is the mean of sample 1, x bar 2 is the mean of sample 2. So we know that x bar 1 equals 36 from the question, x bar 2 equals 25, again it's from the question, and s square p, this s square p is a pooled variance which we calculated in the previous question. So in question 10.8a, we worked this s square p out to be 327.24. That's why we plug that in here, 327.24. Then 1 over n1, so n1 is the number of observations in sample 1, so that's equal to 51, and n2 is the number of observations in sample 2, that is equal to 41. Now there is one more component that we have to deal with, which is t alpha over 2. So is the value of the t-stat for alpha over 2 with degrees of freedom n plus 1 plus n2 minus 2. So here, if you just go back quickly in this question, the degrees of freedom here, that is df, is equal to just the denominator that we have in the formula for sp squared. So the denominator here is n1 minus 1 plus n2 minus 2. So if we just simplify it, it's gonna be n1 plus n2 minus 1. So these degrees of freedom is very important in the calculation, in the hypothesis testing, and also in the confidence interval estimation. Anyway, so in this case, so we have n1 plus n2 minus 1. In this case, n1 equals 51, then plus n2 equals 41 minus 2. So that should be equal to 90. That's the degrees of freedom here. And we have here alpha equals 5% because of 5% confidence interval. So alpha over 2 has to be equal to 0.025 because 5% divided by 2 is 2.5%, which means 0.025. So alpha over 2, alpha divided by 2 is basically equal to 5% divided by 2, that is 2.5%. So 2.5% is equal to 0.025. Now let's go back to the t-table. Where is the t-table? Here is a t-table. Now the degrees of freedom, we have calculated this to be a 90, so it's somewhere between 80 and 100 because the first column, remember, is the degrees of freedom column, df column. So 90 is somewhere between 80 and 100. And then we have alpha over 2 equals 0.025, so 0.025 is right here. That's where 0.025 is. So we scroll down along this column, and the corresponding the t-stat is between 1.99 and 1.98 because 1.99 corresponds to 80 degrees of freedom and 1.98 corresponds to 100 degrees of freedom, but our degrees of freedom is 90, which lies between 80 and 100. So in our case, the t-stat will be somewhere between 1.99 and 1.98. So we can just take the t-stat to be 1.98 because 1.99 and 1.98, they're very close to each other, so it doesn't really matter. Even if you take 1.99, the result approximately will be the same. So let's just go back to our calculation and let's plug in 1.98 for t alpha over 2. So once we plug all these numbers in here, and once we take the plus sign, we will get 18.51. That's the upper bound of the confidence interval. And when we take a minus sign, we get the lower bound of the confidence interval. So the confidence interval of the mean difference, or the confidence interval of the difference between the means of the two populations, is between 3.48 and 18.51. So that's all for today, I guess. So I'll just stop here. If you have any questions, feel free to send me emails if you have any questions. If there's something that's not clear, feel free to let me know. I'll try to get back to you as soon as possible. Alright then, thanks for your attention.